So the last lecture, we're going to talk a little bit more about the transaction pool. This is a fairly short one. It will help you with your assignment though, so pay attention, but hopefully it doesn't take more than 30 minutes or so. And again, afterwards, we're going to go to the training room, or I'll be there. You can come there and ask questions about your assignment. So first, a little bit high level, what is like the purpose of the transaction pool? At the end of the day, a blockchain system is kind of like a market, as in it's providing a service which is processing transactions in a secure way. It's selling block space. It's selling, block space is a good generic word for it. When you learn about Polkadot, you learn this other word called core time. That's like a Polkadot's version of block space. But generally, it's like a market, and like any other market, there could be high demand for it. And if there's high demand, we need a way to deal with congestion. We need a way to if there's many people wanting to put their transactions in, we need to deal with them. And that's the main purpose of the transaction pool. So this image conveys a lot of information. I'm going to walk you over it, so just come with me. Don't go over it yourself yet. So as mentioned, transactions are given to different nodes of the network, whether it's a block author or someone else, through the networking protocol. And how this happens, it's outside of the scope of this lecture, or generally this, what I'm going to talk about. The point is, or what is like the protocol that's used there, I don't know, I don't want to know. Point is, at some point, these transactions are propagated to nodes of the network. And I categorize these transactions then into 3 groups, and they're important to know. I kind of hinted at one of them in the previous lecture as well, but now we're going to go over it again. The first bucket where we keep our transactions, this is actually not a Substrate name, but I came up with it, or I put it there myself. I called it like the Wild West. This is like the transactions that we haven't really we have no idea like whether they're good or not, or like whether they're worthy of being kept or not. This is the least trusted ones. And then there's 2 or 3 options that we can have after this Wild West. So the first is that we do some kind of validation, and you already know that validation happens through talking to the runtime, but I'm not going to repeat it again because you already know it. We do the validation, we realize, this was garbage, we don't care about it. Like, this was a bad transaction, I don't want it, so trash can. We discard it. And there are heuristics and rules around this as well, that we don't then repeat that transaction again. So there's like transaction banning and so on. So if you realize a transaction is invalid now, for a period of time, you don't retry it again. But that's, again, implementation detail. Then the 2 other scenarios that could happen is this 2 other categories I call future or ready, meaning that okay, pause. Okay. Distribute. Sure. But then it's like, I don't know. So but if you look at that monitor, you kind of get the problem. So that monitor is fine. This monitor is scaled. So at this point, it's better if I continue. In 30 minutes, you can come and diagnose this problem. All right. Okay. Let's continue. So then there's 2 categories of transactions that are valid, but there's a difference between them. Some are valid right now, and we call these ready transactions. And in that, I just validated them from the Wild West. It goes into the ready set. It's like it's ready to go. There's another category that's like future, as in it's not bad, it's not necessarily invalid, but it's not ready to be included in the block yet. So in the previous lecture, when we had this diagram and the pool, I said keeps a list of transactions that are ready to be authored to go into a block. I was actually referring to the ready category. And of course, you can also go from this trash can at any point, as in like a transaction might be in the future set, as in, the last time I validated it, it was like okay-ish, but in the future, the next time I try and revalidate it, I realize, no, it's actually invalid now. Sorry, you have to go into the trash can. Same with the ready. A transaction might even be sitting in the ready list, but a block authoring doesn't happen. And we might actually decide to revalidate at some point. Again, we might realize at any point that something was invalid and we throw it away. And finally, this last arrow is what we had in the previous lecture, as in at some point when the block builder wants to actually build a block and does that through the whole dance that we learned the previous lecture, it looks at the ready set of the transactions. So there's with this figure, I would like to teach you that there's two main functions that the transaction pool needs to implement or provide. One is to deal with the validity of transactions, specify whether they are, in which of the three categories they belong to. It's actually like 4 categories. Is ready, future, Wild West, or trash can. To which of these categories a certain transaction belongs, and order them. So within each of these lists, who should be first? Although the order doesn't matter in all of the lists, but at some point it would matter. So for example, in the ready list, when we want to actually build a block, it's pretty important to know which transaction go first. Someone also asked me in the previous lecture about MEV and so on. So for example, if by including one transaction over the other, you can extract more value, these are important things that many blockchain systems care about. So validity and order. Now let's look at each of these in a little bit more detail. Actually, I'm going to do something that will help me. So I'm going to open up my speaker notes and put them next to the slides. You won't be able to see them here, but it's pretty useful for me to know what is my next slide. So actually, it's a bit too small. Never mind, sorry. All right, so yeah, this is again a visual representation of what I just said, as in the point of transaction validity is to shuffle transactions between these categories. So everything starts in this Wild West section, which is like unknown. If it's bad, it goes thrown away. If it's good, when it's ready, it goes into ready. If it's good, but potentially in the future, we put into the future set. Can someone tell me one example of future, for example, based on yesterday's thing from Ankan? Nonce, yes. So a transaction passes all the checks, but the nonce is like future. That's a future. What about a trash can? Like also, in which case a nonce can cause a transaction to be completely discarded? Huh? Yeah, a nonce that is already used, right? A nonce. So if the current account nonce is like 7, but the nonce 5 is gone, so no transaction with nonce 5 is like future. It's actually like gone. It's already been used. Of invalid? Not that I can think of. Not right now, but I'll think about it.
Can you use a mic, please? Maybe you're claiming like a reward that has a block limits after which it's available.
Maybe, yeah. But that could also be just a failed transaction, as in the transaction can go through and it would fail. It's kind of like doing a failed transfer.
Yeah, but after some point it's gonna be valid, so you might keep it.
Yeah, but I'm saying that check, actually that check is crucially probably part of the execution of the transaction, which will not usually happen in the transaction pool checks. I hinted at this already. When you're doing transaction pool checks, you don't want to execute stuff because you don't want to actually execute a transaction and be like, this transaction was a claim reward and that reward is available in that block. So, it's going to be, transaction pool checks are meant to be like very lean and static and easy to do. And checking the nonce is one of the only sort of like things that we do in it. Like, or one of the only, in order to check the nonce, you need to read one data from the state, and that's usually it. Yeah.
So the nonce in the one sec. So the nonce in the extrinsic must be higher.
So if it's higher, it's fine. If it's equal, it's great. If it's smaller, it's already gone.
In invalid state is if it's lower.
Yes. Yes. That's something you should exactly do in your assignment as well. Okay. Can you pass?
When the fees are unable to be paid, are they considered trash or like? Is that transaction considered like trashed or?
It's trash. It's trash. Although it's an implementation detail. Again, all of this happens while communicating to a runtime. I think a reasonable runtime would say, okay, if you can't pay your fee now, come back later. But I'm not going to keep you around in case you become funded.
Thank you.
But you could implement a runtime that doesn't do this. So a few facts about transaction validation. All of them are known. This is just a recap. One is that transaction validation is entirely a function of the runtime, as in the pool doesn't dictate any of these logics or optimizations or so on itself. Like it doesn't, if a runtime is such kind of like a maniac runtime that wants to accept all transactions or whatever, it's possible. That's actually the great thing. Like it's flexibility of Substrate, right? Like if people have implemented novel things or new things using these flexibilities. But yeah, what some of these answers I'm giving is just like a template answer. You could do different things. Transaction validation should be cheap because it's free. So the nodes want to do the bare minimum operation. What's the last thing? Yeah, the transaction pool validation will not change any state. And we call these operations off-chain. I don't know if that's a new word for you or not. Is it? Off-chain, on-chain? Yeah, hopefully it's a word that has hopefully been thrown around a little bit. When we say something is off-chain, we mean it's not actually part of the consensus critical code path. It doesn't lead to any state change. It's some code that's being executed, but it's not like everyone's going to execute it as well and come to any consensus about it. When a transaction pool validation runtime API is happening, one node is doing it, and whatever is the outcome is about that node. That is an off-chain runtime API that is being called. Whereas when you call like that execute block, everyone calls that. Everyone wants to call that. Everyone's going to agree on like the outcome and so on. That's an on-chain operation. The transaction pool is completely off-chain, as in there's no state changes that get persisted. Although you will see this in your assignment as well. You could code your validate transaction runtime API to write to state as well, but those are just going to be ignored. Those state changes are dropped afterwards. Sometimes it's easy. It makes code more readable, and so it helps readability and writability of your code if you just use the same, for example, function that checks if you can pay transaction and deduct it in both execution and validation. But in invalidation, that state changes are dropped. You have a question?
Yeah. From a high level, how does validation different from a traditional, let's say, transfer function to when someone publishes a contract, a transaction that publishes a contract, like for a smart contract, parachain, for example?
So how is the validation of a transfer different from the validation of a...
So let's say you have a transaction that does a transfer versus when you go ahead and submit or publish a smart contract, right?
So yeah, I'm going to try and replay the question to make sure I'm on the right one. So how is that different? A validation of transfer than when you publish a smart contract, for example. So like many of these questions, it's up to the runtime to specify what is my transaction validation logic, and then the runtime could distinguish or differentiate these two transactions, like transfer and publish a contract, and do different things with them. What that is, I don't know. What a reasonable answer, like what I think any sane runtime should do, is actually not differentiate them. I've mentioned this, especially the second point, that transaction pool validation should be cheap, as in it shouldn't like look at the actual operation that's happening under hood and make any decision based on that, or God forbid, it should not actually execute the transaction to see if it's good or not. It should look at high level things like signature, can it pay for itself, and nonce. Actually, that's exactly what you're asked to do in your assignment, right? Check for tip, check for nonce, check for signature. These are the checks that we call like the basic checks that make a transaction worthy of existing, which the terminology in your assignment is that they become applicable, as in like, yeah.
Thanks.
Okay. All right. So a brief look at like the runtime API that enables this for transaction pool validation. We had a look at this in the activity that we had earlier. We found this runtime API, actually, the declaration, and you saw in all runtimes, including in your assignment, that you have this IMP implementation block that actually implemented. And I want to focus further on the return type. That's also relevant for your assignment. All right. Let's go over it step by step. So this, again, we're looking at the return type. It's called transaction validity. And the first thing that we have is that this transaction validity is just an alias for a result. It's a result where the OK variant is like something called valid transaction, and error variant is called transaction validity error. I don't want to get into the error part. That's not super relevant for now. I want to talk more about the valid part, though. So if the result is OK, like a transaction is OK, what are the fields that are going to be returned that are further information about that transaction being okay? So first question, by the way, when a transaction is okay, it means it goes into which list? Ready and future, because they're both okay. But one is okay now, one is okay in the future. And actually, some of these fields that I'm going to explain now specify which one exactly. So the first field is called priority. This is just one numeric value, U64, that is specifying how important this transaction is. Later you will learn that this priority is only used when a transaction is actually in the ready set, but at a very abstract way, maybe the implementation of a custom transaction pool actually interprets it differently, but this is a field that the runtime sets for a valid transaction to communicate with the pool that I think this is the priority of this as a number. So 0 is the least, U64 is max. Again, I want to emphasize that some of these details I'm adding are the details of one particular implementation. But what matters here is that this struct is the runtime's way of talking to any transaction pool. So some teams in the Polkadot ecosystem, for example, have customized their transaction pool. They have likely, for example, interpreted these information differently. Then, interestingly, there's a field called longevity. So this means this validity, this outcome, for how long is it valid? I'm actually not sure about the interpretation. I think it's at milliseconds or maybe blocks. I'm not sure. But it's a number that represents how long is this transaction valid for. So this struct in itself is saying this transaction is valid, but after this amount of blocks or milliseconds, the pool should revalidate it. That's what you use longevity for. For how long is this going to remain valid? And this is where we link back to the fact that I said the transaction pool validation is not like one-off and it's valid forever. It's usually periodic, as in you validate once and you're like, okay, if you're good, I'm going to check you again in 10 minutes. And that 10 minutes come from this field.
Pass the mic, please.
Question. In the assignment, future is one of the variants of the invalid transaction enum. Here, it's suggesting that future is a valid transaction. So that is my question.
All right. So invalid transaction future is used elsewhere. It's actually used in apply. So or when you're actually doing like apply extrinsic. That's an important question. When you are applying a transaction, so when is the time you're authoring, and if the nonce is in the future, that is invalid transaction with future. At the pool level, there is no such thing as to future, because to future you keep it. It becomes it goes into the the.
So the question is, I guess. So deciding that transaction is invalid in the flavor of future would be dependent on the point in which you do this validation. Right?
The point you do this validation.
Like, because there's this method that validate nonce that returns a transaction validity. So the question is, when are you doing this validation? Because,
yeah.
Or you could say like, okay, if it's an invalid transaction of flavor future, and I'm now just putting stuff, taking stuff from the pool and not yet putting them in a block, then I can consider it to be valid.
I got one part of your question that yes, all of this depends on when it's happening.
Yeah,
So
that's
something
what I'm
could be
saying.
valid now and valid in future, or
Yeah.
vice versa.
It's just a bit like being that the code is like that. It's kind of like putting the future flavor of invalid transaction on the error path of the code because it's a. Do you see what I mean?
No.
I'll show you later.
Okay. Next field, it's called propagate. This is, whoops. This is the runtime's way to tell the pool whether this transaction should be propagated to the rest of the network or not. And again, these fields are meant for the runtime to give instructions to the transaction pool, and the transaction pool hopefully obeys them. As in, like, there's no like hard contract between the two. But yeah, there could be cases. This is also again like could be used in like maybe MEV like situations where the runtime is like this is valid, but it's probably best if you don't keep it to yourself. And finally, this is the sort of the most complicated and important one. So let's start from the bottom. Let's establish this type alias called tag, and it's just vacuate, some bytes, opaque bytes. So every transaction, when validated and when declared as valid, has two properties. It requires some tags to be present, a vector of tags, and it provides a vector of tags. And kind of as the name is suggesting, when a transaction requires some tags, it means those tags must be already present before this transaction can go in. And then vice versa, when you're providing certain tags, you can unlock some other transactions to go in by providing the tag. So if for example, a transaction requires tag 1 to be present, it will only be processed when tag 1 was provided by some other transaction. Right? And this could be with this provide and requires, you can basically build a graph of transactions. You can make transactions depend on one another. You can say this transaction can only go in when this and this and this and that have already gone in. And you can already maybe guess what we can build with this. Like when is a situation where we want to say a transaction with tag 4 can only go in when tag 0, 1, 2, and 3 have already gone in. That's basically the non-system, right? So with provides and requires are the primitives with which in your assignment you should build the non-system, which is one of the requirements as well. I'm dropping a lot of hints about the assignments, by the way, so hopefully. Sorry? Tag is just some bytes. Like it could be anything. It could be any. Like whenever we just say vacuate, it means whatever, which is actually pretty accurate because at the end of the day, all other data types are under the hood some bytes. So this is also a vector of bytes. Yes, I will tell later in the nonce case what it should be, for example. Yes.
Yes, Mauricio, in the provides vec of tags. So it means like this transaction will provide tag for other transaction to depend on, right? Yeah. But one thing is it needs first to be applied, and then like for example, there are 3 transactions. The third one, the last one, okay, the first one provides tag, and the last one depends on the tag from those 2 preceding transaction, right? It means like the first 2 needs first to be applied.
But that's actually that's already like I think I can get where that is going, and that statement is already incorrect. As in, like this provide requires is only processed at the pool level. It helps you, for example, you have some transactions. So first of all, remember the context. This is in the context of valid transaction. Some transaction is valid. Does it go into a ready tag, a ready list, or future list? Those that go into the ready list don't have any unfulfilled requires. Those that have unfulfilled requires go into the future list. All right. So it's some information that is only used within the runtime. It's not really at the applied level. Does that make sense?
Used in the runtime.
So, sorry. What did I say? I said used in the pool. Sorry.
Yeah.
Sorry.
Okay. So, but then, okay. So, okay, in the pool, like now it will determine, okay, if this tag has already been reached or not, right? In the pool. Like for example, I think I need to check the tag.
I have an example that comes after this. I think it might help. Like I have an example where, I processed a bunch of transactions. I think it would. Yeah. Do you want to continue or do you want me to continue and
Yeah,
maybe
I'll
I'll answer?
continue.
Yeah, okay. Yeah.
In this type valid transaction itself is not present.
No.
So we keep pair of
That's-
transaction and its validity.
Yeah, that's kept elsewhere. This is only some struct that is describing properties of a valid transaction. It could be, yeah. The transaction is somewhere, but we don't. Okay, one more.
Does the runtime automatically check the requires, or this is like
The runtime sets the requires, actually. So remember, this is the return type of the runtime API.
Yeah.
So the node gives a transaction to the runtime returns this.
okay.
So you are writing a runtime for your assignment, right? So it's actually your responsibility to fill this struct. And your assignment, we ask you to set the priority in a particular way. It's quite easy. And we ask you to set requires and provides such that you're doing like a nonce system. And you can ignore longevity and propagate. All right, I mentioned transaction banning. Details don't matter. The only point I want to get through is that the pools are not naive. I mean, I describe it as like a Wild West, but it's not like it's waiting to be DOSed out with open arms. If a transaction is determined to be invalid, I think the default implementation is that we ban that transaction from ever being even processed again for 30 seconds or 30 minutes. I don't know. Yeah, 30 minutes it seems, but it can be configured. It's a CLI parameter. People can also change this. But yeah, just points that we can defend ourselves sometimes. All right, let's talk more about transaction ordering, this provides and requires mechanism, with an example. So as mentioned, this provides and requires kind of allows you to make transactions depend on one another, build a graph. Let's look at an example. So we have the ready and the future lists, and a transaction comes in. The way I'm representing this is that this is like the name of the transaction, and then you have the list of provides and requires. So where does this transaction go? And this transaction is valid. It's just a matter of is it valid ready or valid future. Where does this go? It's going to ready because there's no requires. So it will look like this. Then we'll have something like this. So transaction comes in, A has already been processed, but this one requires 2 and provides 1. This one goes into the future. Then another one, because this time that it's good to like give you a few more seconds to look at this. So this one provides 1 and requires 2. And the next one provides 2 but requires 3. Still future, because 1, now what we're lacking is tag 1. Because, am I right? Wait, no, what are we lacking? Maybe I think I have a typo here. Was that correct? What was B again? B provides 1, requires 2. C provides 2. Yeah, we're lacking 3. Exactly. We're lacking 3. And once we get 3, everything will be unlocked. Yeah?
Sorry, I don't understand well. What is 1, 2, 3?
So
The
1.
ordering is done. What is this?
You mean like, for example,
The
this?
number 2 means that this transaction provides information for the transaction number 2.
Oh, no. This is like this 1, 2, 3 that we have inside is like that tag. And the tag itself was evacuate, but here I'm just putting one number to simplify
Okay, it's a tag.
Yeah, it's a tag.
Identify some other transaction, right?
It doesn't refer to another transaction. The tag is just some data that we're saying I require this or I provide this, and it could be anything.
Okay, I provide data about the tag 2.
Exactly.
So everybody that requires 2
will be
depends on
unlocked.
me.
Exactly.
Okay.
So for example, here what we've built so far is that. Does anyone else want to speak?
So On the, I guess, on the validation and transaction ordering side, is this where, like, perhaps if we wanted to do something like some custom MEV logic would go?
Yes.
Okay.
Yeah. Especially like with this provides, requires, and priority.
Right.
These are the things that allow you to order transactions.
All right, thanks.
All right, and finally, when we see one that provides one, I think this is where I might have a mistake. I need to double check. But do I have a mistake here? Let me look at this for a second. That's 2. 2 is provided. Yeah, I mean, now the last thing that is required is 3 by transaction C. All right. So this D should have provided 3, but I have it the other way. So unfortunately, this example is wrong. But the point I want to get through is that you could have multiple transactions in your future queue, and they form a chain of dependencies. You know, first guy depends on the second guy depends on the third guy, and once the first guy gets unlocked, everyone gets unlocked with it. So we can, by observing one provides that unlocks a chain, you can move all of them to the other queue. Yes, but I think the example was unfortunately a bit broken. But the point was hopefully clear, as in you could unlock multiple transactions at once. And again, this would apply exactly to your nonce situation as well. So imagine, so by the way, one reason I'm using just these numbers is that if you just imagine this number as a nonce, it's already like a very close analogy to how a nonce system should work. Like you always require the previous nonce and provide the current nonce, and then you can build this chain. Although then you need a way to make this specific to my user, you know, because there's different users on the system. So you probably want to use a tuple of like account ID and nonce. I'll get to that next. But a more concrete example is that, let's say the nonce of a user is currently 2. So the next valid transaction should come with nonce 3. And then you have nonce 4, 5, 6, 7, 8 sitting already in a queue. Once nonce 3 is observed, all of these transactions become valid because the whole chain is now valid, right? 3 is already there, 4, 5, 6 can also be valid with it. Yes?
In this example, the third item requires 2, and the fourth provides 2, so they can go together, or
yep. They get on.
So the order matters
so
in this case.
So I haven't talked about the order of things much yet. Now, so far, it's more about dependency. What goes into future, what goes into ready. Actually, now we can go to the next slide.
But in this case, it's okay to require as long as there's another transaction in the ready state that provides the information.
Exactly.
Right. And what about if there is a loop, like one requires the other and the other requires the other? So the two should go together in the same transaction, the same ready.
I think if there's a cycle, it would just never go through because neither of them. So the condition was exactly correct. Any transaction can go into the ready if there's already someone in ready that provide, like if all the requirements they have are already in ready. So if there's a cycle, okay, I believe it won't. Neither of them would go through. But that's an easy thing to try out, though. You can very easily like code your validate transaction to create a cycle, and then you can exactly observe. There might be, maybe there's a difference, and I'm getting it wrong. All right. So far, we mostly talked about dependencies and when you go from one list to the other, and that last field priority is exactly what would dictate now the order within the ready state. So again, anything can go into the ready when all of the here I'm saying requirements are met. What I meant by it is that all the required tags are already present in ready. Once everyone is in ready, then priority is what would dictate the order, the priority field. Yes. Okay. Oh, it does what? Which parts of this are you referring to?
So the runtime will return the valid thing, and then the node will keep those valid transactions results.
Yeah.
And once they're ready, the node sends the transaction based on the priority.
Yes. Yes. And if priorities happen to be the same, the further tiebreakers are these two items. TTL, as in like the transaction that so let's imagine there's two transactions, both of them have met requirements and equal priority. Then the one who has the shorter longevity goes first. Then if that also happens to be the same, the one that happens to be you have waited longer goes first. So actually, with this information, you can conclude that if you want your pool to really behave like a FIFO, what you have to do is set priority to 0 and longevity also equal for everyone. Because then the tiebreaker always becomes a third one. Then anyone that has been longer in the queue will exit first, and then the pool becomes a FIFO. But this is not a, let's say, a common thing. It's just a question that I got on a previous round, and I thought it's interesting, so I put it here. Okay, and final detail about the nonce. So again, nonce is super important, something that you have learned throughout this course. It's also one of the more challenging parts of the assignment, in my opinion, as in, admittedly and somewhat intentionally, parts of it is not, it's not like spoon-fed to you as you have to implement exactly. You kind of need to explore a little bit yourself. I also highly advise you to look at substrate code and also even frame code. Like, yes, you haven't learned frame, but you can read code. You can kind of find your way around. But I do want to still reiterate some high-level facts about nonce and what it is. So a nonce exists to protect you or fulfill a couple of purposes. Maybe there's more, but this is my interpretation. So it's there to order transactions. Like if a user wishes to send 5 transactions at once, but has a preference on which one should go first, they can convey that using a nonce. It also protects you against replay attacks, and which consequently also then protects you against some kind of double spend, as in if you have 2 transactions that are spending, I mean, this is more of a UTXO thing, but if you have 2 transactions that are spending and they are spending the same money, only one of them goes in because of this nonce system, right? Because they would, in order to be correct, they need to have the same nonce, and one of them will go in, the other one would fail. But replay protection is also quite important, as in if you already have used a nonce, it can never be reused again. We actually had an interesting flaw in Frame, where if an account was destroyed, we would reset the nonce from 0. Then actually, like, the same transactions in the same order could have been replayed, or they can be. But an easy fix for this is that when you recreate an account, you can set the nonce to the current block number or something. But you shouldn't do this in your assignment, just food for thought. Yeah, and the high-level idea, as I said, is this is not the solution, that exactly what you need to do, but it's enough to give you the high-level idea. The high-level idea of implementing a nonce with this provides and require is that you should always require the previous nonce and provide the current nonce. That's like the way you create the sequence. And because, you know, my nonce and your nonce should not influence one another, so you want to like put the account ID of whose nonce it is next to that data, and then use the encoding as your provides and requires.
Question?
Yes.
When do you require and provide? In the transaction pool validation or in the authoring? That's 1. And 2, if you require the previous one and provide the current one, then it's done. Like.
Yeah, maybe.
What do you mean? Like, it's okay, the requirements are already provided, aren't they?
Yeah. I mean, I'm not saying it's like extravagantly mysterious, but yeah. But it's if you already get this, then it's good. You got it.
No, I don't get it.
But to your first, okay.
That's why I have the mic.
All right. So, but to your first question, yes, this is about transaction pool validation. So your first question was that is provides and requires part of transaction pool validation. The answer is yes.
Yeah. So my question is regarding 2 transactions with the same nonce. So they both valid, right? And they will get to the future, but they have the same nonce. And we suppose that only one of them will go to the ready.
Yeah. Oh no. So they can both act. Let me think. So you're saying 2 transactions, both valid, but with the same nonce.
like the same nonce,
Yeah.
and when we do the transaction validation, they both fine, right?
Yeah.
They're not contradict each other.
No. I think so. As far as I know, and again, this could be like an implementation detail of the pool, but they would go as far as I know in the default pool of Substrate, they would both go to ready. But crucially, when you're actually building the block, what would happen then? One of them will have a higher priority and will be put into the block, and it's all good. What happens to the next one? That's when it will get rejected.
Okay.
Right? Because
so it's not possible that both of them will go to the block, right?
oh no, that should not be possible. But I just kind of said why, and I'm not sure if I got it through. Let me repeat.
I understand
okay.
why. It's supposed to be like preserve the order, yeah. But according to the logic, it's valid. It go to the future. It's okay. It will go to the ready. It's in ready. It's supposed to be executed. So that's why my question is when it's supposed to be.
So when you actually execute it, like when you're actually authoring the block, just repeating that for everyone again. When you're authoring a block, you have two transactions with the same none. Both of them are in the ready set. One of them will go first, whichever it is. And that would already bump the nonce of the account. So then the second one is no longer valid. So this is exactly a niche but valid example of when the block author inevitably wastes time. Right? Because the block, like this is why I'm saying block author cannot trust the pool validation, because it happened like long time ago. Pool validation is stateless, as in like, you know, when the pool is validating those two transactions, it doesn't remember that I validated this nonce and this is invalid. This is exactly an example that demonstrates that confidence level. So the block author is kind of like suffering from the pool validation being a little bit dumb. But then once the block is authored, it's all valid transactions. And those who import the block will not suffer anymore.
Okay, thank you.
I want to understand what does mean account and require and provides.
Just the account ID of that particular user, because you can keep in mind that, for example, if my nonce is like currently 7, like it's my nonce. You want these tags to be unique to me. So you need to either prepend or you need to put the account ID somewhere in there such that it becomes unique to me. Otherwise, my nonce is gonna influence his transactions, and you know, like. Do we have more questions, or should I? Okay, one more and then I'll continue.
So I'm wondering about like so if there's like a future transaction that is dependent upon a previous transaction, like a nonce 8 dependent upon a nonce 7, right? And then I submit a transaction with nonce 7. Is that like an actual valid? Because you can submit a nonce, any nonce, right? And it will just go to the future transaction pool. So if I submit nonce 8 transaction and then later on I submit a nonce 7 transaction, at that point, once that nonce 7 transaction is made to be ready, that nonce 8 transaction is immediately made to be ready as well?
It depends. You're not specifying what, with the first transaction in your example, the one with nonce 8, what did it require that forced it to go into the future set? What was it require?
Nonce 7.
Okay, then in that case, when nonce 7 comes, and if nonce 7 has no unmet requirement, and when nonce 7 is about to go to ready, it drags 8 with it.
Oh, right away. So there's no chance for it to like get put into a block before that other future transaction gets made to go ready as well.
It could go in. No, they could go into the same block, but the order that's specified. Because even in that block, it's only valid when it's first 7. And the state is updated, so the nonce of the account is bumped to 8, and then 8 is valid. They could go into the same block, but in the same block, they would still maintain the order that the user wishes.
But they can also go into separate.
They could also go into separate. I don't know if there's a way to communicate that, as in enforce. Like, so the runtime can kind of like pseudo enforce these two transactions must be in 2 different blocks. I mean, it can of course be coded in like in the runtime level logic. So let's say there's a transfer, and whenever the transfer happens, we bump some flag, and we allow that flag to be bumped only once per block, something like this. But I don't think at this pool level there's an API that allows you to specify that.
Mic behind you.
If we were supposed to implement UTXO blockchain, all this stuff wouldn't be like necessary, right? Because the states would be completely different. Like so we would have basically to implement a different runtime for this
of course.
UTXO.
Blockchain. Everything I'm saying is very much biased for account-based blockchains. And I know already from skimming like some of the slides from Module 3 that Joshi talked a lot more about UTXO. But if you want to learn about that, he's still around, and he also knows a lot more than I do. So yeah, but this is all very much account-based, on this account-based system. All right, I have like maybe like two slides left. Maybe it's good to finish those, and then we can have more questions. So yeah, I said this already. Just another recap again. Transaction pool is all off-chain, as in like, you know, no state changes are persisted. Also, one transaction pool called to another. Everyone has flushed their memories. And this also brings me to a kind of like an interesting observation that we have. That is, we usually think the entire runtime is the entire state transition function. The state transition function is the part of the runtime that actually contributes to blocks being produced and state to be transitioned. But in reality, it's not like that. It's actually, there's part of the runtime that doesn't really contribute to the state transition function, as in it doesn't produce new blocks. All state changes are dropped. It's just like for other operations, such as the transaction pool. So you have a diagram that looks more like that. So part of the runtime is the state transition function, but the entire runtime is not the state transition function. If that makes sense. Maybe I should have added like more details to that diagram, where the big circle runtime is what we, or the parts that is in the big circle, but not in the little circle, is usually what we call off-chain operations. Like the things that you talk to the runtime for, but it's not for the purpose of creating new blocks. Whereas the state transition function, the green part, is actually what we call on-chain operations. All right, quick recap of everything. So why we have pools? Because it's like a congested Wild West where people want to compete and people can be malicious. I think those both are equally important. We can't trust whoever is submitting the transactions. But if we are to process them, we also need a way to you know, both validate them, but also importantly order them so we can make the most profit out of it. It's also important to always keep in mind, like, blockchain-based systems exist and work because of this game theoretic mindset where, you know, people do things as long as there's profit for it. And it's the same here. As the miner, as the block author, you want to do things that are profitable for you. The main two tasks of the transaction pool are to validate transactions, which means classify them into 3 buckets. Classify them into 3 buckets, whether they are garbage or they are ready right now and good, they are valid and they are valid now, or whether they're valid but in the future. So that's the responsibility of the validity. And finally, specify the ordering when it matters. So for example, in the ready list, the ordering matters because at some point we're going to use this ready list to actually build a block, and in the block we want, as a miner, we want to put the transactions that yield the most fees, for example. It's like a very common implementation, right? Actually, this is a good thing. So this is a good example. Within Frame, you will easily find the code that is encoding that the priority of a transaction is equal to how much fees it is paying. Or one of the things that contribute is that. So the higher the fee, the higher the priority. Or there many substrate-based chains come with the ability to add tip as well, kind of similar to what we have in the assignment. So basic fee is mandatory. Some tip can go on top, and if you increase this tip, your priority will also go up. And finally, the transaction pool validation is done by the runtime, but is off-chain. It's not part of the state transition function. Okay, so let's, done with lectures. I think I can either take more questions now, a few more questions here, but afterwards I'll go to a training room and we will be there. We come back here at 5 p.m. though. Okay, so let's go with questions now.
I'm just curious if there's any interest in research regarding MEV. within Polkadot or any kind of parachains that you might have heard?
Don't have, unfortunately, don't have anything interesting to share.
Thanks.
So my question is regarding transaction pool. For instance, if some of the transaction meet requirement and it's in ready list, and it provides some tags, and we have some another transaction which is actually requires a provided tag, and it's ready. So it's in one transaction in the future list and another transaction in ready.
Okay.
And one of it is depending on the transaction which is in ready list.
So
but ready is gone. Like it's.
Oh yeah, but what is the scenario you're describing? There's two. So A depends on B. Okay.
Yes.
So there's two scenarios. Either A is in future, B is in ready.
Okay. Yes.
So that is impossible because, as mentioned, whenever a transaction is moved to ready, it brings all of its dependents with it. So it cannot be that A and B are in two different lists. If whenever B goes into ready, it brings A with it. And then there's the opposite where A depends on B, B is in future, A is in ready, and this is also impossible, as in it cannot be.
So it's impossible that this chain would be break and one of them.
No, they move together.
Okay. Yeah. Okay. Thank you. Gotcha.
Okay, good. Then, yeah, let's continue the day, and we'll see you back at 5 here.